In our last couple of videos, we've been looking at classification models, particularly decision trees, random forest, and gradient boosting machines. And for these three models, just to recap here, the benefit of using the decision trees, random forest, or gradient boosting machines is that you can use them if you're unsure what predictor variables you should use, although we've been talking about how it's important to narrow it down as much as possible in order to improve the model. You can use them when your groups are unbalanced. So if you are trying to predict a label south, not south, and you have a lot of people in your training data that are not south and very few that are south, then it's a better classification model than, say, K nearest neighbors. The other benefit is decision trees. We can visually show the relationship when we have more than two predictor variables, and we saw that as we looked through the tree. And then the random forest, the benefit was that if you are overly concerned about false negatives, then it helps to deal with that. And if you have very large data sets, then you use the gradient boosting machine. But decision trees, random forests, and gradient boosting machines are highly susceptible to what's in the training data. They are highly influenced if you're loading in variables that are unrelated. And we tried to improve that model by doing things like random forests instead of decision trees, where we average tons of decision trees instead of one, but then we lose that visualization ability. Or gradient boosting machines tries to speed up the process while improving the accuracy by adding trees. So we need to then look at how do we improve the performance of decision trees, random forest, and gradient boosting machines, all three of them. Well, to do that, we need to tune our hyperparameters. So when it comes to the decision tree, you have decisions you can make. For example, and I showed this before, I'll just see if I can move my face here. We make decisions about when it can branch from one node, then it branches off. So what's your opinion about the location? If it's positive, we have a branch. If it's negative, there's a branch, and we go to a next question in the survey. Well, we can make decisions about things like the minimum number of sample we need before it splits off into branches again. So we can actually tune the hyperparameters by specifying things like the appropriate depth, how many layers do we get, what's the minimum sample before we split. These are all hyperparameters. These are all decisions we make, or we use the built-in default values for the decision tree. Well, they influence the output, and so we want to make sure the decisions we make about those things are the ones that create an optimal and more accurate output. So we're going to tune the hyperparameters. Well, how do we do that? We can use something called grid search CV to help us find the optimal max depth. How many levels should be in your tree? And to find the minimum samples leaf. This is the minimum number of data points after a split. Okay, so after the branching, it's the minimum number of data points. And the minimum sample split, which is the number of data points necessary to even split the group. So minimum sample split is before the branching happens, and then the minimum sample leaf is, can you identify that as a subgroup? Well, that's going to be dependent on what's the minimum number of sample respondents in that group to make it identifiable. So these different parameters or hyperparameters, we can tune it by running multiple runs of the decision tree and look at if it changes the optimal max depth, the minimum samples leaf, the minimum sample split. What does that do to the accuracy? And then it finds the optimals for the hyperparameters. Okay, so to do this, we're going to have it run multiple times. Well, the other thing we need to do is use what is called K-Fold cross-validation. K-Fold cross-validation lets us train our data on what we call K-1 groups, and then test on that one group that's withheld. So if you think about, for example, let's say we can take our database and divide it into 5 groups. We then pull out one group to be the test. Well, we could run it again and train everything but a different group and then have it be the test. and then run it again where we pull out a different group to be the test. And so with K-fold cross-validation, we keep pulling out a different group to be the test group, and we train the algorithm on the remaining to see how sensitive it is to what is in the test group and what is in the training group. Okay, so we're going to do that.
Once we have tuned our algorithm by improving our hyperparameters in order to get the most accurate model that we can, when we're using random forest or gradient boosting machine, the problem with those is that they create no visual. So the decision tree, right, we could see how it made the decision as to what label each individual group of individuals had. But with random forest, where we are averaging the trees, and gradient boosting machine, where we're adding the trees, there is no output that is visual. So we're going to use something called feature importance to help us identify which of the variables are actually impacting the algorithm. And so we're going to create a graph that you see like this using the built-in with sklearn. And it's going to then identify or rank the variables by the amount of influence they have on the model. So we're going to create one of these in our...
So we're working through our classification Python workbook. Just a reminder, you can find this workbook at drstephpowers.github.io/BIA. We are working on the one that says classification. We are towards the very bottom of the worksheet. Make sure you grab, as you click in here from GitHub, the appropriate Excel files and link your Python workbook in Google Colab with the Excel files you put into your Google Drive. All right, let's go in. So let's start by tuning some hyperparameters. So what we're going to do is we are going to look at the binary classifier of south, not south. And so if you haven't already, so if you're using a fresh Python workbook, this is your first video, or you closed it after the last video. So if we load here df2.head, if you load that and you find you don't have the south column here because you're just using the fresh data from your Excel file, you will need to create the south column by copying over df2 question 23, renaming it south, and then coding it to be 0 for north, 1 for south, 0 for east. So if you don't already have this column, then you'll need to run this code right here. We already have it because we've done that a couple times now. We're going to need to import some packages. If we are doing our decision tree, we need decision tree classifier. So we'll just do the basic decision tree here and tune our hyperparameters. So from sklearn.tree, import decision tree classifier. You'll notice we didn't import just tree from sklearn import tree. You need that one if you're going to graph and show the visual. And here we're not going to show the visual. We're simply trying to improve the model. So we want to measure the model's performance. We're going to use train test split to split the data set. And we are going to find the accuracy score. And then because this is a binary classification, south, not south, we'll do precision score, recall score, and we'll do our receiver operating curve as well. All right, let's load those in. You'll notice here this last one, grid search CV, that's going to help us tune those hyperparameters. All right. So we're going to do xtrain, xtest, ytrain, ytest. We're going to pull in those same variables we've been using in our previous videos. We're going to use our binary classifier south. And we're going to do our 80-20 split. So we're testing 20%. We are training 80%. We'll do a random state of 1900. That's the one we've been using previously in these binary classifiers if you want to be able to compare. We're going to stratify by the south to make sure that there are south, not south in both the testing and the training data. So let's load that. Okay. We have our decision tree classifier that does the basic decision tree. So call the model, fit the model, predict. And so without any tuning of hyperparameters in this particular scenario, we get an accuracy of 69%. We have our precision score here of 67% and a recall score of 40%. We can create our receiver operating characteristic curve. And so we can see here that, remember, the better it is this curve, this point here, this elbow should be up on the top left. So not particularly good. We have here that our true positive rate is sitting really here about 40% and our false positive rate here about 15. So it's not a particularly good model at this point. The question is, can we improve it? So what are our options? Well, we can look at a number of different scenarios. So we could change the max depth. And I think when we looked at it before, I think we had about 5 was the depth that we were looking at originally. So let's look at a range of depths. What if we have a very simple model with just 3 rows? What if we have one with 8 rows? So just to, I'm going to take you back. So this was, yeah, this is the multi-label one. Let's go to the one that is the, so we had this one, for example, here, this decision tree, that random state 1900, so same data set. And if we looked at the tree that it outputted, it is 1, 2, 3, 4, 5, 6. It's got 7 levels, 7 depth. Okay, so this one had 7 depth. So what we're going to do is look at a range. So how much? So 1, 2, 3. Maybe it's very simple and stops here, or maybe it's more complicated and adds, 2 more levels to that depth. So let's go back. So we're going to have it go through and test. What if we allowed more depth? What if we allowed less depth? And so to do that, what we're going to do is we are going to say max depth can go from 3 to 8, so test those out. And then minimum sample split, let's just go back to our little info thingy here. So when we talk about minimum sample split, this is the number of data points necessary to split the group. So if we're looking at that tree, just find an example tree here. How many have to be in this sample in order for it to be allowed to have these branches off of them? Okay, that's the minimum sample split. And then we have our minimum sample leaf, so the minimum number of data points in the resulting group after the split. So when we look at these, you see how there's 10 here, there's 1 here, 2 here. In order for these to exist as a subgroup, is there a minimum number? Okay, here it just allows for 1. So we can set that. Let's go back into our code. So minimum sample split, let's say 2, 3, 4. So we're going to look at, it can split off. If it gets down to just 2, it can split off if it is 3, 4. You could provide quite a larger range if you want. And then minimal sample leaves, that remaining subgroup can have just 1. What if we make it just 2, 3, 4? You can create as many different combinations as you want here. So we specify the parameter grid. It's going to go through and iterate through these different scenarios. So load it in. We're going to do a grid search CV where it's going to take D-tree. That's the model you just created here. Okay, so it's using this data set, our random state 1900. It created this model D-tree. We are going to go through that, and then it's going to look at the parameter grid, okay, and specifying our parameter grid here. Oh, come back. Okay. And then what we see here with our grid search CV, it's using our decision tree model. It's using these different hyperparameters. And then the CV that you see here is from that cross-validation. So when we say CV equals 5, what it's going to do is it's looking at essentially the scenario we had showed here, where this cross-validation where we have it split into 5. Okay, so the idea here is to check these hyperparameters, but not just check the hyperparameters with one test and train set, but by taking subsamples from it and changing out what is test and trained. Okay, we are going to fit this on our data, and we're going to have it find out what hyperparameters are the best parameters. So let's run that. It says the max depth should be 3, the minimum sample should be 4, and the minimum sample split should be 2. That as it runs through those iterations, that's the best option. So what we do then is we do our decision tree using our decision tree classifier, and we specify those hyperparameters in this. So just like before, we did a max depth equals 5 to kind of simplify one. Here we're going to take the tuned hyperparameters and stick them in. So we're going to call our model, but now with specific hyperparameters. We're going to fit that model. We're going to predict based on that model, and then we're going to check the accuracy. And so if we do a comparison, here was our accuracy, 69.23. Here's our accuracy here, still 69.23. All right, precision score, did it improve? Still 67%. And recall score, still 40%. All right, I'm gonna guess this ROC curve probably looks the same. All right, so given the parameter choices that we gave it, those parameters here, it couldn't really find a better setup than what we already had. Okay, you can, depending on what your data set is, you can see drastic improvement. So it's always good to do this to kind of fine tune that model to see if you can eke out a bit more accuracy from it using these methods. So perhaps we need to consider more here. Just remember that as you expand this, it takes a bit more time to run. Let's see, just see if it does any better. Probably not. Okay, find us here. Again, more scenarios, longer it takes to run. So just keep that in mind. We're running it here in our Google Drive. It did come up with a different result. So look, it says max depth 7 and minimum sample leaf 1 and minimum sample split 3. Let's run that. Let's see if we can eke out some more accuracy. Okay, predict. Okay, 69.2 is what it was before. 69.2 is what it's here before. And looks like there's no difference. Okay. So different combinations seem to get us about the same results in this particular scenario. So in this case, if we're not able to eke out any more accuracy, again, I would go back to the variable choices and see if we can improve, excuse me, the model with different variables instead. All right. What we have here is using that K-Fold cross-validation score. You can look at your model, your decision tree, and we can import what is called K-Fold and cross-val score. And so with this, what we can do is we can look at how it's performing if we use different test and train. So from sklearn.tree, import our decision tree. This is just the basic decision tree, not the random forest, but you could trade this out for random forest or gradient boosting machine. And then here we import K-Fold and cross-val score. So we can then run that. And we would do is we would add in here that we want to do K-folds. And we can look at it here, our model, with splitting it into 5. So we call the model. We're going to do K-folds where we're going to split 5. So we're just naming it that it's going to be 5 splits. And then what we can do is we can have it give us a cross-validation score from the model that we've created here, our decision tree. And in this case, the command here for the cross-validation score has here's our variables. Here's what we're predicting is south. And then our CV, that's the cross-validation. So you can see we're doing this cross-validation without the hyperparameter tuning, just the cross-validation by itself. So we can say, give us the score, and then find us the mean. And so here we can see how well it performed with our cross-validation. So with the default hyperparameters, we get a cross-validation score of 81%. Okay, it's not an accuracy measure, but what we can do then is we can look at if we tune it. Let's tune it twice. Let's do it with this combination here. Was that the original one? From the original run, this is with a depth of 3, the leaf of 4, and 2, and then we'll run it again with the new one it just outputted. So let's try it here. We have our hyper-tuned decision tree. We'll do a K-folds, 5 here, and then we'll get our cross-validation score. And so we can see if it has improved any with that hyper-tuning. And we can see, just as we saw, the accuracy didn't change. We can see here the cross-validation score doesn't change. Let's just go and grab with this particular, let's try this one, the second run we got here when we expanded the options, and see if we get a better cross-validation score. I'm going to guess not, simply from the fact that the accuracies didn't change. And so since the accuracies didn't change, the cross-validation score wouldn't really be improved either. Oh, a little bit. So what this is saying is that even though that accuracy, that precision, recall weren't any better with the decision tree, according to our cross-validation here, that this new hyperparameters of 7, 1, and 3 is a slightly better model if we're starting to change out what is tested and what is trained. So we can look at this cross-validation score to see if the score improves as we tune the hyperparameters. And this is then saying, okay, well, let's change out what we're testing and what we're training. What do we got here? You can do what is called a stratified fold. So what we were doing before was just the K-fold. Stratified fold, in that case, what we're doing here, the K-fold is just randomly selecting, it chops the data set into, in this case, 5, because that's what we told it, number of splits, and it is randomly doing it. With the stratified K-fold, so our K-fold cross-validation, so stratified K-fold instead of just K-fold, then what we're doing is that we're making sure that we have that stratification over the south. So when we do the train test split, we were doing stratified equals south. This is to ensure that in that cross-validation score, it's also doing the same thing. It's maintaining the fact that there's south, not south in both locations. So if we run that, then we get our cross-validation score here at 82.6. If we then run it with our tuned hyperparameters, this was the first scenario here, then we get a cross-validation score here. Interesting. It doesn't like the max depth 3, the sample leaf 4, the sample split 2, when we make sure that our train test is stratified for the south. I'm just going to go back in here and grab these. Let's see if it performs better here. Let's try this one instead. So we have stratified, just like we do in our test and train. We have the tuned hyperparameters that are grid CV suggested. And now let's see if we get a better cross-validation score. And it's about the same as we were seeing those different scenarios. So it looks like in this particular case, this particular model is about tuned as well as it can be. So we can use K-Fold and Stratified K-Fold to get a cross-validation score to compare different models with different hyperparameters. We can also, as we did previous to that, just look at the accuracy, precision, recall of that. Now, before we leave this, in terms of tuning and understanding our random forest and gradient boosting machine, because the things we just did, we could have also done with the gradient boosting machine or random forest, didn't have to just be the decision tree. You can do these with all three. They all have the same hyperparameters. So what we want to do is we want to figure out what features it's using, particularly for random forest and gradient boosting, where we can't actually output the decision tree. So you need to install something called SHAP. It's not already in Python, so you're going to want to install it. So pip install SHAP, and then we import it. And then I'll show you as you go through. So as we build our classifier, in this case, a random forest classifier, again, we would test and train, and this is just that binary classifier we've been using. I don't have a random state on here, although I could. I'm going to call the random forest classifier. I'm going to fit it. Okay, I'm going to predict all these phases as I would go through just the regular classifier. I would get the accuracy, this accuracy of this one. I removed that random state. I didn't like that random state of 1900. So it picked something else here, and it gives us a much better accuracy. So random state 1900. That one was not performing well.
Suppose that you've done a random forest classifier and you want to know which of the variables were used in that classification model. So what we need to do is we need to run our random forest classifier, which means we're going to need our random forest classifier from sklearn.ensemble. And we're going to have it separate out the training data and the testing data. So we'll do train_test_split. And we are using our accuracy score here, of course, because this particular example is a binary classification, south or no south. We could also look at precision and recall and all those that we've looked at before. What we're adding to this is that we are going to use matplotlib.pyplot as PLT, and that is going to give us the graph that we saw previously, and we'll import pandas as PD. That should already be running. We ran at the very beginning of the workbook, but just in case, we'll have that here to allow us to modify the data. So we're doing this from work that we had done previous, so just make sure you are df2.head. We should see that new variable that we've created a couple times now in this workbook where we've added the south column. And if you don't have that south column, then scroll up to previous sections. Somewhere in here is where we added that column, just running back here in time. We see it every couple, but you see this command here, right? We added the variable south and we replaced the labels 1, 2, and 3 with south or not south. So if you don't have your data frame with that new column, make sure that you run that. All right, scrolling back. Okay, so what we want to do is we want to do our random forest classifier, normal process as we had before. So we're going to split the data into train and test. We have question 2, 13, 14, 15, 18, and 20 that we're going to use to try to predict whether it's south or not south. We're using our 80-20 rule, so 20% is going to be test. And we're stratifying over the south to make sure there are south and not south in both the training and the testing data. We call our classification model, we fit it, so standard process as we've always done. We predict just like we've done before, and we can calculate our accuracy. What's different here is the next couple steps, and this is where we're going to need to pull the feature names. those feature names are going to match here what you have used as your variables that you're trying to predict your label with. So we are simply copying the names here, not the actual columns of data, but the names. So you'll see here it doesn't say data frame 2, it just says that here we have a list and it contains Q2, Q13, 14, 15, 18, and 20. Then we're going to have a call from our classification model, something called feature importance. So this RFC is the name that we gave our model here. Okay, so if you gave it a different name, you'll need to change that out. But then this feature importance is an item that it creates. So we want to just call that. And then the other thing we can look at is here we can have use NumPy. So we'll make sure NumPy is running as well. And we can do the standard deviation. And so it's looking at the variability, because remember with the random forest classifier, we are creating default 100 different trees. So what we want to know is what are the most important features or variables in the model. And what we want to do is look at how it changes. So we're looking at that standard deviation here. Now, what do you do with all this? Well, what you do is you do a command here using pandas. So we're going to do panda.series, and it's going to create a series from that importance information and index it on the feature name. So we're attaching the importances to the different variables. And then we're going to create a plot. And that plot is going to plot those importances, and it's going to make a bar chart. The error here is going to be the standard deviation, and we'll give it a title such as feature importance. So really you can leave all this as is with everything that's named as long as you have your RFC is what you labeled your, if we have RFC importance here. Did I label, where's my RFC importance? RFC importance here, pulling from importance. So if you can leave all this as long as this is RFC importance, then this is RFC importance, and this importance here matches this one. So you could really just keep all this code as is and just change out the variables if you're running this with a different set. So we find the feature names and the standard deviation, we plot our graph here, and what we see in this particular set is that of the 100 different trees, question 18 was the one that was used the most in these different decision trees. It had the most impact. And if you'll recall, question 18 was about whether the workplace felt safe. So likely what's happening is the south location doesn't feel safe. And so it helped discern between south and not south. The second most influential question was question 15, which is how satisfied are you with your location? So it makes sense that the two of those would have the most impact on the algorithm.